Hey, this is a video having to do with projectile motion. We're going to spend much less time on projectile motion this year than you did last. Basically everything we do will be review. And what we define projectile motion as is things that move only under the influence of gravity. That means we're going to be neglecting air resistance. Now the result of that is that the acceleration is equal to 0 I hat minus 9.8 j hat meters per second squared. And that means that the x component of the velocity is constant, and the y component is just like free fall. The result is that the equation of motion for the x is delta x equals vx times t, where t is the amount of time since the launch. And then, on the other hand, for delta y, we can use the kinematic equation, v naught y, the initial y component of the velocity, times t minus 1/2 gt squared, where g is equal to 9.8 meters per second squared on Earth. If you go to a different planet, gravitational acceleration might be different, and that would change your equations a little bit. Well, the equation is the same, one of the numbers would be changed. And then you can also use the other two kinematics for y. You can say that the final y component of the velocity equals v naught y, not plus, but minus gt, and also that vy squared minus v naught y squared equals negative 2g times delta y. So instead of having something like 6 different variables to worry about, more than that actually, 10 different variables, we only have 5. And so when you work projectile motion problems, it might be useful to use a table. In the x direction, you have the x velocity, which is constant, so we don't need final and initial. You have the x displacement, how far it's gone horizontally, and you have the time, nothing else, because you know that ax is 0, and therefore that the initial and final velocities are the same. Now in the y, you have the full complement of kinematic variables. The initial and final velocity, the delta y, meaning total up and down displacement, and then you've got t, and then you know that the y component of the acceleration is negative g. So you've got 6 different variables really, because t is the same for both of them. And then depending on what you know, you pick your equations and you solve the problem. Now here's a quick example. This is something thrown horizontally, and you've got a dart. It's thrown from a height of 1.6 meters above the floor. The bullseye is 1.4 meters above the floor and 3.7 meters away. So like good physicists that we are, the first thing we'll do is we'll draw a picture. We'll try to figure out what exactly this question is asking. So here's the floor. Here's the person throwing the dart. There's the dart. Here's the dartboard. There's the bullseye. What we're told is the dart starts at 1.6 meters above the ground. The bullseye is 1.4 meters above the ground. Okay, that shouldn't actually be the same. So I'll redraw the person. Trying this again. There we go. And the path the dart takes will be parabolic. It will curve downwards slightly after it's thrown. What we want to know is the initial speed of the dart. Now the idea here is that if the dart's thrown too slowly, well, it takes a certain amount of time to fall through these 20 centimeters. And it needs to be going at exactly the right speed that when it's fallen 20 centimeters, it's moved 3.7 meters horizontally. Now because the initial velocity is horizontal, that tells us that v naught y is equal to 0, and vx is the component, the x component is the same thing as the dart's initial speed. So that's what we're looking for. And now we go ahead and make our table. We say v naught y equals 0, vy we don't know, delta y is negative 0.2 meters, and t we don't know either. Vx is what we're looking for. Delta x is 3.7 meters, and again we don't know t. Since we're looking for the x component of the velocity, we're going to be using the equation for x, which basically says delta x equals vx times t, or vx equals delta x over t. The problem is we don't know what t is. So what we've got to do is use the y equations to find t. And we're going to use the second kinematic, because we don't know the final velocity in y, and we really don't care about it. So we'll say delta y equals v naught y is 0, plus, or not plus, but minus 1/2 gt squared. And we know g, we know delta y, so we can find t. Thankfully it's not a quadratic, although some of them will be. 2 delta y over g, square root. And then plug that into this equation, which gives us vx equals delta x times the square root of g over 2 delta y. Plug in numbers, 3.7 meters times 9.8 meters per second squared. Oh, there should be a negative sign here. Over 2 times negative 0.2 meters. And we'll get a calculator, and we find that the initial speed has to be 18.3 meters per second, which is pretty fast, but not totally unrealistic. At this point, the questions I'm going to check tomorrow are questions 3, 5, and 8. That's questions, not problems. You should be able to do most of the problems in chapter 4 at this point, though.